So this is the 15th session on relative velocity. Okay. Sorry, rigid body kinematics, not rigid velocities. Rigid body kinematics. Okay. So in this, I'll take up the concept of rolling motion. Okay. When we are familiar with the word rolling, everyday life you are observing so many cases of body rolling over other. Okay. So that will take up that case of rolling motion. Okay. So first, what we'll do, we'll define what is rolling motion. And then we'll say that there are two types of rolling motion: rolling with slip and rolling without slip. Okay. And then we'll define both these types of rolling motion from mathematical point of view. Okay. In terms of kinematical conditions of velocities of the contact points. And then we'll take up numericals on this topic. Okay. Fine. So first, what we'll do, we'll take the case of, we'll define what is meant by rolling motion. Okay. See, rolling motion. So we are familiar with the word rolling. You see, so many examples are here. For example, we'll just take the case of rolling motion examples. For example, suppose this is a fixed ground. This is the circular drum, side view of a circular drum. This is the center seat is moving rightward and the body is rotating. Okay, so it is moving like this. This is what body is undergoing rolling motion over the horizontal surface. Example of rolling motion. For example, you are riding a bicycle, and the wheel of the bicycle is undergoing a rolling motion, as seen from ground frame. Or for example, you are driving a vehicle, and the wheel of the car is moving. It's undergoing a rolling motion with respect to ground. Okay. For example, a train is moving on the tracks. The wheel of the train is undergoing a rolling motion over the railway track. Okay. Or suppose we have a plank. Plank is moving in like this with respect to ground, and the body is rotating and center is shifting over the plank. So this body is undergoing rolling motion over the plank. Okay. Or we can take other examples of rolling also. For example, see like this. We have suppose we have a disc which is rotating in a vertical plane about its horizontal axis, and other wheel is moving like this. Center of the wheel is, another body is over this body, and center is moving downward and it is rotating. It's coming like this and going this way. It is rolling over this body. So these are all examples of rolling motions. Alright, these are all examples of rolling motions. Other examples also we can take. For example, like this. This is an inclined plane, okay? And a drum is moving like this. Drum is undergoing rolling motion over the inclined surface. Center is moving downward and it is rotating. And center is shifting downward. This wheel is undergoing rolling over this inclined plane. So these are all examples of rolling motions. Alright, fine. Now one more point you must note down. See, so how do you formally define rolling motion? That is the point. How do we formally define what is rolling motion? So we can define in this way. Suppose we are given two rigid bodies. We can take any of these examples to define rolling motion. We can define rolling motion in this way, like this. That suppose there is a rigid body B1, okay? It's moving another rigid body B2. This rigid body B2 may be a translating body, or it may be a rotating body, or it may be a fixed body. It can be anything, okay? Fine. So these two are rigid bodies, B1 and B2 are rigid bodies. B2 may be a fixed surface, it may be a movable body, translating plank for example, or it may be a rotating body itself, okay? So B1 is said to roll over B2 if following conditions are fulfilled. Rigid body B1 is said to roll over B2 if following conditions are fulfilled. Okay, fine. I got this one, fine. First condition, B1 and B2 are in mutual contact in a given time interval under the interval of observation. Throughout they are in contact, mutual contact. B1 and B2 are in mutual contact. Are in mutual contact in the given time interval. Second condition is what? Second condition is B1 should rotate with respect to the frame under consideration. B1 rotates with respect to the frame under consideration. Under consideration. Third, the center of the body should also shift. It's not that B1 is moving like this itself with center fixed. No, center should also move, advance. Okay, the body B1 should shift as a whole. Okay, should shift as a whole. Body B1 should shift as a whole. Body B1 should shift as a whole. Okay. Body B1 should shift as a what? Whole. As a whole it should shift over the body B2. When these three conditions are fulfilled, we say that body B1 rolls over B2. Okay. And as I said just now, B2 may be a fixed surface. It may be a translating body, translating plank, or it may itself be a rotating body. Fine. Alright. So these are the three conditions to be fulfilled. Okay. So that rolling can be defined in this way. Fine. Now I rub this one. Now one thing you must note down. See, when B1 rolls over B2, then in general at different instants of time, different material points of the two bodies come in mutual contact. This point is an important point to be observed. When B1 rolls over B2, then in general at different time instants, different material points of the two bodies B1 and B2 come in mutual contact. So when B1 rolls over B2, then in general at different instants different material points of two bodies come in contact. Different material points of two bodies come in mutual contact. Okay, this is a point to be noted down. This is a point to be observed. Fine. Then, in general, different material points of two bodies come in mutual contact. Different material points of two bodies come in mutual contact. In general, at different instants of time. I'll just demonstrate this concept. Okay, like this. See, imagine a plank moving on a horizontal ground, sliding, just translating plank, rectilinear translation. Okay, and this is the drum which rolls over this plank. Now see, at certain instant T1, material point D1 and material point P1 of the plank are in contact. Center, this is the center, this moves like this and this rotates clockwise, this body. At time instant T1, material point D1 of the drum and material point P1 of the plank are in mutual contact. Fine. After some time what happens? This body goes ahead, this also plank goes ahead. After some time the body drums comes here. Say T at T1 plus delta T. At this instant of time, material point D2 of the drum and material point P2 of the plank are in mutual contact. And by this instant D1 has come somewhere here and P1 has come somewhere here. Okay, and still some time later what happens? The plank has moved still further. Drum also has come here. D1 has moved still up. D2 has also moved up. Now D3 and P3 are in mutual contact. Okay, so what do you observe? At different instants of time, different material points of drum and the plank come in mutual contact. Okay, at T1 plus 2 delta T, at this instant D3 and P3 are in mutual contact. So at T1 time, D1 and P1 are in mutual contact. At T1 plus delta T, D2 and P2 are in mutual contact. At T1 plus 2 delta T, D3 and P3 are in mutual contact. Okay, so in general the 2 points of contact change for 2 bodies in general. Okay, fine. So this I have defined rolling motion. One more observation regarding rolling motion I have given. Alright. Now I rub this one. So this much I have told you. Fine. Now rolling can be categorized into 2 types. Rolling motion can be categorized into 2 types. One is rolling with slip and second is rolling without slip. Rolling with slip and rolling without slip. Rolling without slip is also called pure rolling sometimes. Rolling without slip is also sometimes called pure rolling motion. Alright. And rolling with slip, sometimes we say impure rolling, but generally we don't use that word. Generally rolling with slip we say, okay. Now see, one thing which is common in both these cases is that in both the cases the two bodies are in mutual contact. Okay, fine. In both the cases, one thing which is common to both of the types of rolling is that the 2 bodies are in mutual contact in that time of observation. Okay, fine. So this point should be kept in mind. Now our aim is this: to write down the mathematical condition for these 2 types of rolling motions. Okay, fine. So there is one property which is common to both of them. In both types of rolling motion, one mathematical condition is true for both these cases. What is that? That I'll just state here. Okay. This I'll rub it, fine. See, one thing which is common to both of them is this. Suppose this is a body B2, okay? And this is a body B1. Okay, fine. Now suppose these 2 bodies are in contact, mutual contact in the time interval T1, T2. Okay. Now we take at certain instant T, which belongs to this interval. We take a certain instant T which belongs to this time interval T1, T2. At this instant, material point P1 of body B1 and material point P2 of body B2 are in mutual contact. This is the common tangent plane at the contact point, and this is the common normal at the contact point. Alright. This is the common tangent plane at the contact point, this is the common normal at the contact point. Assume that the velocity of P1 is V1 and velocity of P2 is V2 with respect to some frame under observation. Now V1 makes an angle of theta 1 with the common normal and V2 makes an angle of theta 2 with the common normal. Okay. Now see, B1 rolls over B2, meaning in this time interval T1 to T2, B1 and B2 are always in mutual contact. At certain instant t, P1 and P2 of the two respective bodies are in mutual contact. Now, component of V1 and V2 along common normal will be what? Component of V1 along common normal will be V1 cos theta 1. Let us call it as, say, V1 perpendicular, say. Component of V2 along common normal will be what? V2 cos theta 2, which is equal to V2 perpendicular, say. Alright. Now, what I am saying is, three possible cases arise. Either this is more than this, or this is more than this, or they are both equal. Okay. Now, what I am saying is, if V1 rolls over V2 in this time interval, then at each instant of this interval, component of velocities of 2 points of the two bodies in contact along common normal are always equal in magnitude and direction both. That is a statement which I am telling. That is, I am claiming that any instant, for all instants of this time interval, component of velocities of the 2 points of the two bodies in mutual contact along common normal are always equal in magnitude and direction both. So I am claiming in this that these two have to be equal. Why? Because if they are not equal, then either the bodies will separate or one body will pierce into other. This I explained just now. See, if V1 perpendicular exceeds V2 perpendicular, what will happen? Tell me. Component of V1 along common normal is V1 perpendicular. Component of V2 along common normal is V2 perpendicular. If this is more than this, then this P1 will move up and P2 will move up a lesser distance. The bodies will separate. Is it not right? If this is more than this, then this body will separate from this. B1 separates from B2 in this time interval. B1 separates from B2 in this time interval. But bodies are not separating in this interval. They are in mutual contact. So this cannot be a possible case. Fine. Now if V1 perpendicular is less than V2 perpendicular, what will happen? V2 perpendicular is in this direction. V1 perpendicular is also in this direction. If this is more than this body B2 will pierce into body B1. That is, break and enter into body B1. But that is also not happening. So this also cannot be a possible case. Because if this were true, then B2 pierces into B1. B2 pierces into what? B1, which is not happening. This also cannot be possible. This also cannot be possible. There is only one thing left. What is that? V1 perpendicular is equal to V2 perpendicular. That is, V1 cos theta 1 is equal to V2 cos theta 2. Fine. So, what is the one thing? Since V1 rolls over V2, therefore in this time interval at each instant, V1 and V2 are in mutual contact. Therefore, at any instant t of this time interval, component of velocities of the 2 points of the two respective bodies in mutual contact along the common normal are always equal. Okay? Because if it was not equal, either the bodies will separate or the bodies will pierce into other. But neither both of them are not happening. So only one thing is possible. What is that? Component of velocities of 2 points of the two bodies in contact along common normal should always be equal in magnitude and direction both. Okay? So for each instant of this interval, this condition is going to be fulfilled. Whatever 2 points of two bodies are in contact, for those 2 points, this condition will be satisfied. Okay? This is a condition common to both of them, rolling with slip and rolling without slip. Fine. So now this I'll rub it. Now, we take the case of rolling with slip and rolling without slip. So first we take the first case of rolling with slip. See, you are familiar with the word slipping. Slipping word is familiar to everyone. Simply this is a body, one body, this is another body, going like this. This is slipping over this. This slip kar ja raha hai. This is slipping, okay? So rolling with slip. So see, I'll draw the diagram again which I rubbed here. Okay. This is the body B1. This is the body B2. This is the body B1. This is the body B2. At certain instant T of the time interval T1, T2, material points P1 and P2 of two bodies are in mutual contact. This is the common tangent plane at the contact point. This is the common normal at the contact point. Velocity of P1 is V1. Velocity of P2 is V2. V1 makes an angle theta 1 with the common normal. V2 makes an angle theta 2. This is the tangent plane at the contact point. Now, rolling with slip also. Rolling with slip. So now, in this one thing is true. Is common which I just discussed here. And that is that V1 perpendicular is equal to V2 perpendicular. At every instant, this instant also it is true. V1 perpendicular is just V1 cos theta 1. And V2 perpendicular is simply V2 cos theta 2. So these two are equal in magnitude and direction both. Now rolling with slip, that is P1 slips over P2. That is rolling with slip. But the component of velocity of P1 in common tangent plane is how much? V1 sin theta 1. And component of velocity of P2 in common tangent plane is how much? V2 sin theta 2. Now since P1 slips over P2, so therefore V1 cos theta 1, V1 sin theta 1, V1 sin theta 1 is not equal to V2 sin theta 2. Let us call this term as V1 parallel is not equal to V2 parallel. So this is the case of rolling with slip. Okay, fine. So in rolling with slip, this condition is going to be fulfilled. But this condition is not going to be fulfilled. So in rolling with slip, what will happen? Component of velocities of 2 points along common normal, they are equal always in magnitude and direction both. For whichever two contact bodies are in contact. And second, component of velocities of 2 points in contact and belonging to two bodies along common tangent plane, they are not equal. Then only slipping can take place. No? If for example, if these two contact points P1, P2 have the same velocity in the tangent plane, then they cannot slip. They'll move together. So that will be rolling without slip. But we are talking of rolling with slip. That is, one is slipping over other. If this is like this, then V1 parallel is more than V2 parallel. If it is like this, then V2 parallel is more than V1 parallel. In both the cases, slipping will take place. That is the case of rolling with slip. Fine. So in rolling with slip, only along common normal the velocities are equal. Along common tangent plane, the velocities of the 2 points are not equal. For whichever instant we are considering. Okay. This is one case. Rolling with slip, I told you. Fine. Rub this. Fine. And next is rolling without slip. Next is the case of rolling without slip, which is also termed as pure rolling, as I mentioned here just now. Pure rolling, which is also called, just as I mentioned, pure rolling. Rolling is without slip also one thing is common. What? Two bodies are in contact in the given time interval. So at each instant of the interval, this condition is going to be fulfilled for whichever 2 points are in mutual contact. So this condition is going to be fulfilled here also. For all t belonging to the time interval t1, t2. But see, it is rolling without slip. Now P1 is not slipping over P2. This is possible only when component of velocities of P1 and P2 in tangent plane are always equal in magnitude and direction both, for whatever 2 points are in contact. So in rolling without slip, V1 sin theta 1 is equal to V2 sin theta 2 for all times belonging to what? T1, T2. That is, V1 parallel is equal to V2 parallel for all t belonging to T1, T2. Okay. So in rolling without slip also two conditions are fulfilled. First, this condition is fulfilled and this condition also fulfilled. In rolling with slip, only one condition is fulfilled, this one. In rolling without slip, both conditions are fulfilled. This also and this also. Fine. So now if you write this in vector form, then V1 perpendicular vector is equal to V2 perpendicular vector. And if you write this one in vector form, V1 parallel vector is equal to V2 parallel vector. If we add these two terms, if we add these two equations both sides, then what do we get? V1 perpendicular plus V1 parallel is equal to V2 perpendicular plus V2 parallel. Now this is just the vector V1, velocity of point P1, and this is just the velocity of point P2, velocity of V2. Okay, so in case body B1 rolls over B2, pure rolling, then at any instant of time, velocities of the 2 points for the two respective bodies in contact are always equal in magnitude and direction both. And this statement is valid at each instant of this time interval t1, t2. Okay, fine. So in rolling without slip, rolling with slip, only component of velocities along common normal are equal. In rolling without slip, component of velocities along common normal and along common tangent plane, both are equal. And this will imply that velocities of the 2 points of the two respective bodies in contact at that time interval are equal. Okay, so this is rolling without slip and this is rolling with slip. Fine. This alphabet, okay. Now one more thing, rolling is a universal condition. If B1 rolls over B2 as seen from some frame F, then as seen from some frame M also, B1 will appear to roll over B2. So rolling motion is a universal condition. Samjhe? Is it alright? Rolling is universal. That is, if B1 rolls over B2 as seen from some frame M, then as seen from some other frame F also, B1 will appear to roll over B2. If B1 rolls over B2 as seen from some frame M, then as seen from some other frame F also, B1 will undergo pure rolling. Pure rolling motion. B1 will undergo pure rolling over B2. Okay. So this was the 15th session on rigid body kinematics. This chapter was wholly dedicated to the discussion of rolling motion, which I have discussed fully. Okay. And the 16th session on the rigid body kinematics, I'll take up examples on rolling motion. Alright. I'll take up examples on what? Rolling motion I'll take up. Fine. This I close it here. Fine.